yesterday, what we discussed was we saw that, well, we introduced a matrix product state as a one-dimensional array of tensors with some, there was this periodic boundary conditions maybe, or open boundary conditions. And then we started studying in which sense this was an efficient representation of wave functions, the number of parameters that we needed to specify to get the wave function of n spins was proportional to n, not exponential in n. And then we also saw that it was possible to efficiently manipulate this wave function in the sense that we could compute the norm of this state, or we could compute evaluate expectation value of a local observable with a cost which was, again, proportional to n. Okay? And then in the tutorial, I think that you had as an exercise to see how to go from this fourth power of chi to a third power of chi, and that's actually the way this is the optimal way of manipulating this tensor network. Okay? So hope you enjoy that during the tutorial. So today I want to continue. I want to explore in which sense, now that we have this class of wave functions that we can efficiently specify and manipulate, we'd like to understand whether these wave functions are useful for anything. And again, what we'll do in order to gain insight into the answer to this question will be to study two properties. We'll study how correlations scale in these ansatz and how the entropy, entanglement entropy, scales in these ansatz. And for that, it's convenient to go to a specific setting, which is that of a translation invariant wave function. So remember, if we take a matrix product state with periodic boundary conditions, that means the last tensor is connected to the first one, and we assume translation invariance, then we can choose all the tensors to be the same. Okay? And this is the type of state, matrix product state with periodic boundary conditions and translation invariant. That's the one that we would like to study, or that we will use in order to understand how correlations decay in this variational class. But I want to be clear that we will not specify what tensor A is. So tensor A is full of variational parameters. There are chi squared times d variational parameters sitting there. We will not specify those. Okay? That you would specify those by trying to minimize the energy of a given Hamiltonian, but we will not do that. We will take just this as our variational class, and we'll see that there are properties that follow just from the structure of the variational ansatz, okay? Without referring to specific choices of values for these tensors. So this will be a property that is true for any MPS of this form. And so let's do that, but first let's quickly review, because we need the notation. Let's quickly review how we computed the norm, or in this case, the scalar product of psi with itself. And this was simply put psi as a ket, psi as a bra, and contract all the indices. And we saw that this could be expressed as some transfer matrix that I'm going to call M, okay, which is A star, yeah, complex conjugate. So this transfer matrix to an nth power, and then take the trace. That's what this expression is saying. Okay? And it will be very useful to decompose this transfer matrix in its eigenvalue decomposition, which means in terms of right and left eigenvectors, with the eigenvalues being here. So what do we mean by left eigenvector? So the left eigenvector multiplying the matrix from the left will give rise to the left eigenvector times the eigenvalue. That's the expression that we will be using in a minute. So that's just the diagrammatical representation of this equality here. And the same for the right eigenvector. The right eigenvector times the matrix acting from the multiplying from the right will give us the same eigenvalue as before times the eigenvector. Okay, so what we will be needing here is to understand how to take, or what the power of this transfer matrix is. And the power P of this transfer matrix M is just that has the same eigenvalue decomposition, but you replace the eigenvalues by its power P. Okay? That's normal. And what we'll observe is we'll assume that we have organized the eigenvalues in decreasing order, at least the absolute value of the eigenvalues is organized in decreasing order, and we assume a gap between the largest one and the second largest one. Okay, that's an assumption we're making here. Okay, and if that is the case, then we can see that when we expand this sum over all that are chi-square terms, remember this matrix here, M has two indices to the left, two indices to the right. So as a matrix, that's chi-square times chi-square matrix. So it has chi-square eigenvalues, okay? And what we see is that this sum is dominated by the first term when we take the power p, okay? So the reason being that if lambda 1 is strictly larger than lambda 2, then lambda 2 over lambda 1 is an absolute value is smaller than 1, and when you take sorry, there's something missing here. When you take a large power of this, this number goes to 0 exponentially fast with p. Okay, so we can approximate. We can just take approximately the first term, especially that we will be taking the n to infinite limit. Okay, so all this p will be infinite, and then that's definitely something we can neglect. Very good. So we know how to compute the norm. The norm is going to be, at that point, just lambda 1 to the nth power plus corrections that are exponentially suppressed with n. Okay, and we take n to infinite, then we're left just with lambda 1, the largest eigenvalue to the nth power, and then we'll just normalize the tensor A such that lambda 1 is equal to 1. Okay, so we'll take the largest eigenvalue to be equal to 1 by normalization of the wave function. All right, and from now on, lambda 1 is going to be equal to 1. So what we saw then is that we could efficiently compute the norm and therefore normalize the wave function. And the point was that the cost here involved here did not depend on the system size n, so we can do it even for n infinite. And then we were ready to also compute expectation values of local observables. We also saw that yesterday. So the tensor network changes from this one to this one, where this guy is a local insertion acting on a single spin. Then what we get is that we replace the trace of transfer matrix to the n with a trace of transfer matrix to n minus 1, because this guy does not look like the transfer matrix, and we just include this guy here. Okay? And in this case, we already argued that, well, we can decompose. What we're going to do is we take the n infinite limit. So this is going to be we can replace the whole transfer matrix to the n minus 1 power by the leading term. Remember that lambda 1 is 1. And so this will look like the trace of the right and left eigenvectors times this guy. But now taking this trace, the trace means we can shift this to the other side, and we're left with this simple expression where this is tensor A, this is tensor A star, and this is just the right eigenvalue 1, the dominant one, and the dominant left eigenvalue. Okay? So this is the very simple expression you are left with when you try to evaluate a local expectation value. You don't need to do anything here. This was just derivation. Computationally, you just go to this expression. Okay? So if you want to evaluate the expectation value of a local observable with a matrix product state, you just contract this small tensor network. Good. So we saw that yesterday, and now what we want to do is to argue that using similar expressions that the correlations in a matrix product state decay asymptotically at long distances exponentially with the distance. Okay? It will be exponential decay of correlations. And we will see that the derivation, to understand that, we actually need to follow again this type of discussion. Somebody changed the menu here? Oh, here. Okay, so what we want to do now is we want to study correlations first. We want to study these structural properties of the MPS variational class. And we'll start with correlations. So we're in part C. We want to understand whether this is a good approximation to something, maybe to ground states. Okay, and what we do is we start with correlations, 2-point correlators. And what I did here is I wrote what a 2-point correlator is. I'm going to assume that we have this MPS with periodic boundary conditions that n, the system size, is infinite. Okay, so I write the MPS like this, but you have to imagine there are infinitely many copies of tensor A, and then we'll look at the distance between the two insertions, which is going to be finite but large. Well, for the time being, just finite. So this is an insertion on site 0, so I'm going to put a tensor, a matrix here, and this one is at site L, which is going to be somewhere here. Okay, so what we're saying is that in between we have M, the transfer matrix, okay, to the L-1 copies of it. Okay, very good. On the outside, what we have, so the total number of sites is n, which will be infinite, and what we see is that if we count how many, the rest of copies of the transfer matrix that we have between this and there it's the transfer matrix to the n minus L minus 1, okay? And the two missing, so we want L minus 1 and n minus L minus 1 to add together to n, except that we have these two insertions, right? These two insertions give us matrices which are not the transfer matrix in here and in here, okay? So when we take n to infinite for fixed L, this thing here, this transfer matrix to this infinite power, can be replaced with the dominant left and right eigenvectors again. And so that's what I'm doing here. I'm going to put the insertions. Okay, we have L minus 1 copies of the transfer matrix in between, and this I've just replaced the. I've just introduced the dominant left eigenvector with eigenvalue 1, and the right dominant eigenvector. Okay? So I hope this is clear that we didn't do any approximation or anything. We just took the n infinite limit, and we were left with an expression for the 2-point correlator of this form. And if you wanted n to be finite, then the corrections would be exponentially suppressed in n. But when we take n infinite, this term is not there. Very good. So now what we want to do is we want to understand this expression. We want to understand how this expression, which is our correlator, scales with L. And what we can do again is to, we realize that these are copies of the transfer matrix. So we're going to come here and replace. So you can think of this as you have some vector, and n copies, or L minus 1 copies, sorry, of a transfer matrix. Okay, that's a number. We want to see the structure of this number, the dependence of this number on L. And for that, what we're going to do is we take the transfer matrix and we replace it with its eigenvalue decomposition to the L minus 1 power, and we just get this expression here, where again we have the two vectors, one to the left and one to the right. Okay? Good. Now we want to, it is convenient to, this decomposition runs, it's a sum over all the eigenvalues. Remember, there are chi-square eigenvalues. And now we're going to split the sum into two pieces. The first piece, we'll only consider alpha equal to 1. So, oops, wrong color. So let me see. Let me draw this once and for all, so I don't need to do it again. So what I'm saying is we have chi-square terms here, and we just put the first one, we separate it from the rest. The eigenvalue lambda equal to 1 is 1 already by normalization, so there is no factor here. This is a number times a number. And here we have still a sum of chi-square minus 1 terms. Okay? And there is a sum of objects. So this would be the right eigenvector alpha. This is the left eigenvector alpha. And this is the right eigenvector 1, and so on. Okay? So we know all these objects. This is A star. The point is that this is just some number, okay, that I'm going to call, I'm going to take this thing. I'm going to call it C alpha. I'm going to take this other tensor network, which is another number. I'm going to call it D alpha. And I'm going to pay attention to this thing, which is some power of L. Very good. So we have this first term and that second term, which is a sum. The reason to split them apart is that this term here actually corresponds to the expectation value of the first observable times the expectation value of the second observable. Okay? If you now come and look at the connected correlator, okay, the connected correlator is the expectation value of the two insertions minus, oh, nice. That's wrong. Okay, so there is an expectation value here as well. Okay, we subtract the product of expectation values, and that just corresponds to taking whatever expression we had there and subtract the first term from it. Okay? So we're left with just the second contribution, more painting, more drawing. Okay, so what I'm saying is we're left, the connected correlator is just this sum. And this sum is what? This sum runs from alpha equal to 2 to chi square of lambda alpha to the L minus 1, and then some constants. Okay? So let me just write it. Let me write it this way. It's a sum over exponentials. This clearly is these are exponentials in L. And now what I'm doing is I'm just grouping together all the constants that I find in the way, C alpha, D alpha, and I just want to get rid of this minus 1 here. Just not nice. So I divide by lambda alpha. If I divide by lambda alpha, if I include this minus 1 in here, I'm left with just lambda alpha to the L. And so if I define some correlation length C alpha as being just 1 divided by log of lambda alpha, I need to check this expression. I think that this is correct. Then we're left with the final expression we wanted, which we need to interpret now. Okay? But I insist that this is before we even talk about what variational parameters we have. We can express the correlators in this way. So this is a sum of exponentials, okay? Exponentially decaying functions. So you have a sum. You can play around with that. If you now consider, so variational parameters will go into determine these mu alphas, these correlation lengths. But by construction, remember that lambda 1 was equal to 1, and lambda 2 was promised to be smaller than lambda 1, at least in absolute value. Okay? And so this guarantees that these expressions decay. These exponentials decay with a distance. Okay? And if you have a sum of exponentials that decay with a distance and you want to know asymptotically how this looks like, well, there will be some exponential that decays slowest. Okay? And that would correspond precisely to, by construction, by demanding that the absolute values of these eigenvalues of the eigenvalues are ordered, this will correspond to the one who has the largest real part, maybe lambda 2. And so what we conclude is that at long distances, okay, we have the correlation, we have log of L, and maybe let's take the log of the correlator, and maybe for a while it will do something, okay, that may, if we want, through the variational parameters, we may manage to mimic a power law, but eventually it will decay. It's guaranteed to eventually decay exponentially, okay? And this will happen, roughly speaking, when the largest correlation length, when we reach system sizes, or sorry, L is on the order of the largest correlation length. Okay, so this very much looks like what we had in ground states of one-dimensional Hamiltonians with a finite energy gap. So is that clear? Is this calculation clear? In the end, what we're saying is a two-point correlator is the result of multiplying together many matrices, okay? And each time you multiply by a matrix, this two-point correlator is diminished by a constant factor. So the more matrices you have in between, the more constant factors you have in the correlator, and that automatically gives you this power, this exponential decay. Good. So what I want to do next then is to study the entropy. And for that, you can go to figure 4 of the notes I gave you for yesterday's class. And so what we can do is, we're done with correlation, so entropy, or entanglement entropy. What I'm going to do is I'm going to draw the MPS. I choose, again, with periodic boundary conditions. So this is the ket now, the bra. I'll also draw the ket. Okay, and now we want to take the trace over some subset of spins. Let's say that we want to keep for our region A. Let's say that our region A contains these 3 spins here. Okay, and so we need to trace out the rest. Okay, and now we would like to see whether just from this is what this is a tensor network representation for the reduced density matrix on the region A. Okay. So we have, again, an efficient representation for this density matrix. And now what we would like to see is whether we can establish an upper bound, or whether we can characterize the entropy of this density matrix just from the shape of the tensor network. And the way to do that is illustrated in figure 4. What it says, what figure 4 says, is that this thing may look like a mess, but in the end, there is a way of detaching, of rewriting this such that it looks like this. Okay. We are not worried here at the moment about computational cost. We just want to understand how many connections we have between the top and the bottom of this tensor network. And so we can split it in this way. Okay? And now all we need to do is to look at how many connections we have between the bottom and the top. So what we see is that there are 2 connections. Okay? And so what we already argued yesterday, and I think tomorrow's tutorial has some exercise just to review this, is that it follows. So remember, each index here, these are Born indices. Each index goes from 1 to chi. Okay? So it follows that the rank of rho is at most chi squared. Okay? The product of the sizes of these 2 indices. The number of non-zero eigenvalues of this reduced density matrix is at most chi squared. Okay? So we will have some probability distribution of eigenvalues, which will be P1, P2, P chi squared, and then zeros. Okay? In general, this density matrix may have, this one has dimension d to the 3, but we'll see that It may be arbitrarily large, but only at most the first chi-square eigenvalues are going to be non-zero. Why? Because, again, as I said, the upper part and the lower part of this density matrix, of this tensor network representing the density matrix, is connected only by two indices. But now you realize that this was for region A of size 3, but what if we had a much larger region? Okay? So we would have this part here. We would have the lower part. And then we would have the rest of the wave function with, we would trace indices and so on. Okay? So I'm considering the case where now region A is much larger. But in the end, when you draw the whole thing with many connections, I'm going to argue exactly in the same way. I'm going to argue that I can split this density matrix into two pieces. Okay? And that the only connections between the branched parts of the density matrix is given by two indices. Okay, so now I would have to draw something with many more legs. But in the end, there are only two connections between the upper part and the lower part. Okay? We see that this bound on the entropy does not depend on the size of region A. So the conclusion is that the entropy as a function of the size of the region, when we plot it in semi-logarithmic with the x-axis in logarithmic scale, will maybe look like a log, but for sure at some point it will saturate to a constant. And this constant is going to be at most. So what we know is that this entropy as a function of L is at most log 2 of chi squared, or 2 times log of chi. Okay? So remember, the entropy was of a probability distribution with chi square non-zero values, was upper bounded by the flat distribution on chi square values, which would be a distribution that looks like 1 over chi square, 1 over chi square, 1 over chi square times. Okay? And the entropy of this is is log of chi square. You take the 2 outside. Very good. So this also looks, this upper bound, this constant entropy, also looks like what we have in ground states of gap Hamiltonians. Okay? So there we are. Turns out that the matrix product state, it doesn't follow from what I said, but it turns out when you try to use a matrix product state to represent ground states of gap Hamiltonians in one dimension, it turns out that it's an excellent approximation. It offers a very efficient approximation, okay? To close to machine, actually practically machine precision. And if you want, you just use more digits in your calculation. You can approximate brutally well a ground states of one-dimensional gap Hamiltonians with a matrix product state. Here we've only built some intuition for it. We've seen that the correlations decay as they decay in the ground state of gap 1D Hamiltonians, and that the entropy saturates to a constant in the same way as we had in ground states of 1D gap Hamiltonians. Are there questions about this? Okay. So now what I want to do is it turns out that the matrix product states maybe were introduced to simulate ground states of 1D gap Hamiltonians, but they are useful for many other things. And to understand that, I want to do, so far I've been looking at, we fixed bond dimension chi to a constant. Okay? Remember, the bond dimension did not depend on the system size, and that's what made these ansatz efficient, right? That's what made the cost be linear in the system size. Now I want to do something else. I want to think of a matrix product state with arbitrary bond dimension, so I'm not going to fix the bond dimension. And I want to argue that you can use a matrix product state to actually represent any wave function in the Hilbert space. Okay? It won't be an efficient representation because the bond dimension will grow in some exponentially actually in the system size, but we will see that the matrix product state is nothing but a sequence of singular value decompositions of a tensor. So for some reason, this is 11.4. Don't ask me why. I want to relate matrix product state and Schmidt decomposition. I want to go back to make a very clear connection between this tensor network and the entanglement that we have in a wave function. So I'm going to be working with matrix product states with open boundary conditions this time. So we don't connect the last and first tensors. And I want us to consider a generic wave function, which for concreteness I'll take to have, I will assume that it only has 5 legs, just to make it concrete. Okay. And remember what we had for the singular value decomposition of a matrix M that was of the form U, S, Vidal. This contained the singular values. And U and V were unitaries, or more generally, this time we'll take them as isometry. So what we'll do is, remember this. Okay, so let's assume that this is small m times n, this matrix. So now I'm going to take a decomposition where this one is the first matrix m times chi, okay, where chi will be the number of the Schmidt rank, the number of non-zero singular values. Then S is going to be chi times chi, diagonal, and V is going to be chi times n. What I'm doing simply is I'm removing any dimension in this intermediate matrix that contain only zeros. Okay, so I'm going to assume that we have S1, S2, S chi, and I've thrown away additional dimensions that will be empty. So what we have in general then is that this is matrix chi times n. So it's going to look like this, and then here we have m. So in general it could look like that. Okay. So again, this would have been a unitary matrix, but I threw away everything that was not contributing at all because there were zeros here and the same here. So this is what I call U, and this is what I call Vidal. Okay, so let's take, what I want to do is I want to take this wave function and first consider its singular value Schmidt decomposition or singular value decomposition with respect to taking 1 on one side and 2, 3, 4, and 5 on the other side. Okay? So what does this mean? Well, it means that I'm going to assume here, I'm going to take 1, 2, 3, 4, 5. I'm going to write it as one matrix, some matrix of singular values, and 1, 2, 3, 4. I just took this, I looked at it as a matrix with one index here and another index which is the product of those 4. And this is nothing but U, S, and V diagonal. Okay? Is it clear? You can always do that, right? You take your tensor of coefficients and you look at it as a matrix according to the partition. So this is S, VD, looking at this as a matrix where we take 1 on one side and 2, 3, 4, and 5 to be the other part of the other index of the matrix. And I'm going to use a property in a second that says that actually, if you have one from this decomposition, it is obvious that if I take the wave function Okay, this is U S Vidal. If I take the wave function and I multiply it here by V and Vidal, okay, V times Vidal is not the identity, it's a projector. But when V and Vidal multiplied by the wave function, it does not change the wave function. Okay, what I'm saying is this has dimension chi, which we don't know how much it is at the moment. This is d to the 4, and this is d to the 4. And when you multiply V times Vidal, right, you get some object acting on 4 sides. But this is not the identity, okay? Because it has only rank chi, which in general is going to be smaller than d to the 4. Nevertheless, this is just some projector into some chi-dimensional subspace. But when you apply it to the wave function, it's trivially identity because what we do have is that this Vidal times V, this is the identity on this subspace, okay? So we do have that 1, 2, 3, 4. Okay, this is Vidal and V. This is the identity on this chi-dimensional space. So what I'm saying is because this is the identity, then we can remove it. Okay, and what do we get? We get exactly the same expression that we had before. So this confirms that I can go here, I can come here, and take psi. That's clearly an identity. And what I just argued is that I can multiply by, by what? By Vidal V. Sorry, V Vidal. And that is still the same wave function. But automatically, this means I can write this in this way. Okay, so I'm going to contract these two pieces here. This guy becomes this guy, and this Vidal is right there. So what I've done is I've broken the wave function, okay, into two pieces, right? And now what I want to do is I want to take this tensor and do the same. I want to break it into two pieces. And I can do this sequentially. So what I would use now is a partition. The next thing I have to do is I take this object and I look at the decomposition, so SVD, between 1 and 2, and the rest, 3, 4, and 5, okay? And the net result, so there will be some isometries and so on, so let me continue here. What we've seen so far is that this ended up being something like that, okay? That was through an SVD and 1 and the rest. Now, if I use an SVD of this object between this index and this, that corresponds to 1 and 2, and then 3, 4, and 5, then I'll get that this object becomes of this form, okay? And now I take this object and I apply also an SVD and so on. And before you notice, you obtain your MPS. Okay? So what I'm saying is that any wave function of n sides can be written in an MPS form. The only difference between what we've been doing so far and which meant fixing chi from the start to some fixed value, and what we're doing here is that here chi on each cut that we have is determined by the Smith rank of the wave function on that cut. Okay, so we cannot impose a value of chi. We just have to ask the wave function how many terms we have in the Smith decomposition between left and right according to this cut. And so generically, we know how much this chi is going to be. Okay, it's not going to be a constant. So So let's look at this for a generic psi in CV to the n. What we have is that we'll get an MPS where if we look at this, this is dimension D, okay? So generically, chi will have to match this dimension, okay? This is chi 1. Now, when we look at the Schmidt rank in this partition, remember, if you take random states, what I'm saying is if you take the random state on a bipartite system, generically, it maximizes the Schmidt rank. Okay? So what's the maximum rank that we could have here? Well, this is a bipartition of, we have D square system times a D n minus 2 system. Okay, these are the dimensions. And always the Schmidt rank of a random state will maximize the smallest of the two. Okay, will be the maximum of the smallest of the two. So we have chi square equal to D square. Okay. Chi 3 is going to be D to the third power, and all the way to half of the system. And then on the other half, we'll start descending, and chi n minus 1 is going to be D. Chi on the partition n minus 2 is going to be D squared, and so on. So what we see is that in the middle of the chain, so let's assume n to be even for concreteness, and what we have is that right in the middle of the system, this partition, this corresponds to chi n over 2, okay? That's going to be, well, what do we have here? D to the n half, okay? So this is going to be D to the n half. Now, what we see is that, yes, we can represent any wave function with a matrix product state if we're willing to consider a bond dimension which is exponential in the system size. Okay? So basically, let's look at this. Let's take this tensor and let's look at its size. This tensor, this index takes values, takes D different values. This one here takes, we just argued, D to the n half values. The previous one takes D to the n half minus 1 values. Okay? So what's the size of this tensor? Well, let's look at the size of this tensor, just the product of the sizes of the indices. So what do you get? You get D to the n. Exactly as many parameters as this wave function. Okay? The MPS is not making any magic here. If you want an exact representation of any wave function in the Hilbert space, you can have it in the form of an MPS, but the MPS itself is going to contain the same number of parameters as the whole wave function. Just a single tensor contains D to the n coefficients. Okay? So the picture we want to have is this. The Hilbert space, we've been complaining, it's very large. Okay? And the MPS, this tensor network, offers the possibility of considering just some subregion. Maybe this subregion corresponds to chi equal to 3. Okay? If you fix the chi, then you get only access to some subregion of the Hilbert space. You want more? Get a larger chi. Okay? Chi equal to 20. It includes all the smaller chi's. Okay? Now, you want the whole thing? Fine, you can have it. But chi is going to be D 2 n half. And there is no gain, no computational gain. Okay? You cannot use an MPS efficiently in that case. So MPS can be used both as a strategy, as a variational answers to restrict your attention to some subset of the Hilbert space, and there be able to manipulate the state efficiently, okay? Or as a concatenation of singular value decompositions, which is true of any tensor. So you can always take a tensor and singular value decompose it according to different cuts, and that will give you an MPS. But then there will be no efficiency gain. You don't gain anything computationally from doing that. Okay? And the amazing thing, though, is that when you restrict your attention to finite bond dimension in some value of chi, which does not depend on the system size, you still get some submanifold here, which is of interest because it happens to be an extremely good approximation already to ground states. Remember, ground states are not generic states. They are very special. They live somewhere, and it happens. Where do they live? Well, they actually overlap with this MPS representation at fixed bond dimension chi. Very good. And I hope it's clear from this discussion that the connection, the way we understood actually that matrix product state was a good approximation to ground states was precisely by studying what happens when we decompose, when we perform a Smith decomposition on a ground state. That's what you did in the second week, right? You realized that you had that the entropy of these bipartitions was not following. So we had this plot. This is log L, entropy. And we saw that that the generic state, so let me put L here instead, a generic state was linear, and then that the ground states were doing something really weird, almost log or constant. Okay, so that is exactly what you need, the extra ingredient that you need in order to understand why for ground states, instead of saturating the bond dimension to the maximum value, you can replace it with a smaller value. Okay. Very good. So I want to use the last 10 minutes to tell you that, okay, so yeah, we have the ability to represent efficiently ground states of gap systems in one dimension, but actually the MPS is nowadays being used for many other things. And the key actually is what I said before, that maybe increasing the bond dimension, maybe not leaving it as a constant, but growing it slowly is already enough to represent ground states also, for instance, for critical systems. Sorry, this is not the one I want. Okay, so it turns out that in practice, the MPS can be used for many more things than just representing the ground state of a gap Hamiltonian in one dimension. And so, for instance, let's study 1D critical systems. What we said is that we saw that the correlations as a function of L were the sum. In the 1D critical, the correlations should be a power law, right? We mentioned this last week. And that the entropy should scale as a log. Now, the MPS cannot do that. Fine. But let's repeat this plot here, but now in logarithmic scale for, say, the correlations. Okay? This is what the critical system looks like. That's what we would like to do. And this is how an MPS for a finite bond dimension can do. Okay? So you put chi equal to 20, and you have a sum of exponentials. Remember that the correlations were a sum of exponentials, and that the variational parameters would determine all the coefficients that we had here. Okay? So these mu's and this correlation length, they can be changed by changing the variational parameters. Now, we can actually, with the sum of exponentials, we can approximate many things. We can approximate a power law decay, okay, to some distance. And eventually, you'll see that you actually have a sum of exponentials, and the largest correlation length will kick in, and you'll see that this was not a power law. But at short distances, you can emulate a power law. Now, if you're not happy with this approximation, you want to get closer to the ground state of the critical system, well, use a larger chi. Larger chi, it's going to emulate, say, this is chi equal to 30, okay? It's going to allow you to approximate the power law for longer. And then eventually, yes, it will decay to an exponential. It will become clear that it's an exponential, okay? The same can be said about the entropies. What we would like to have is this, log of L. Now, an MPS with finite bond dimension can be used to do something like that, okay? So eventually, there is an upper bound here. It will go to a constant, and this constant, it's going to be, so for chi equal to 20, this constant has to be smaller than 2 times log 2 of 20, okay? Now, if you're not happy with this approximation, you can go and increase the bond dimension of the MPS, and that will allow you to go to to saturate to a constant, which is again upper bounded by 2 times log of 30, a larger number. Okay. So what we see is that we can systematically improve our MPS description of approximate description of a gapless of the ground state of a gapless system, of a critical system. Okay, so this is one thing you can do with an MPS. What I want to say about this is that tomorrow we'll see an ansatz that naturally reproduces the power law without having to systematically increase the bond dimension, and naturally reproduces the logarithmic behavior of the entropy without, again, having to systematically increase the bond dimension. Good. So, but as a practical tool, if you don't, you can still use an MPS to study critical systems. So what else can you use an MPS for? Well, it turns out that there is, you can use it for excited states. Okay. Okay. So we've been talking about ground states, but you may want to also study low-lying, low-energy excited states. And the way you can do that, and it's done in practice, is through an ansatz where you fix the momentum that you want by hand, and then the ansatz looks like this. For the ground state, we would take A, many copies of A, a same tensor. We would optimize it to minimize the energy. And now what we're going to do instead is we're going to consider an ansatz where we come here and replace. So A, we fix it as in the ground state. Okay? And what's an excited state? An excited state is creating locally an excitation, but then to get good, well-defined momentum, we have to take linear combinations where this excitation is in different places. Okay, so let me consider a situation where I take a linear combination of matrix product states I take this linear combination, but I put a phase, given precisely by k, by the momentum, every time while I displace the operator B. So what I'm saying is this B, okay, is we determine it variationally, will contain something that is different from A in this neighborhood, in the neighborhood of this site. This corresponds to an excitation, localized excitation, and then the rest of the system is in the ground state, as represented by A. Okay? So you could imagine having an infinite system here, if you want. A would be the tensor network for the ground state. And then you consider replacing one tensor with B, and that accounts for an excitation. And what we do is we put now a linear combination of where the wave function I just described with the local excitation, right? So this one here corresponds to having the ground state everywhere and then some localized excitation. And now what we do is we consider having the excitation, a linear combination of having the excitation here and there. Okay? Nice. So this excitation is traveling, and then we add this phase. So there is a phase 1 here, phase e to the ik here, phase e to the minus ik here. And that guarantees that if you now take this linear combination, okay, and act with the translation operator on it, you get back the same wave function. But overall, there is a phase e to the ik that spits out. So this wave function has well-defined momentum. Okay? So MPS can be also used to describe efficiently this type of excitation. Very good. So I'm now just listing things. Maybe I can do this here. So the next thing is you can also simulate time evolution. So not just ground states or lower lying excited states, but we could also consider starting from a state at time 0 that has an MPS description. So imagine you have an efficient MPS description for a given state. And then you would like to understand this state, or the evolution of this state in time. Okay? So it turns out that there are efficient ways of simulating this evolution for as long as the evolved state also has the nice conditions that it has a small amount of entanglement. So if the initial state of a quantum system has only a small amount of entanglement, has an MPS description, and if during the time evolution this condition of not having a lot of entanglement does not change, then we can actually efficiently simulate the whole evolution. Okay? And the way this works is we represent the initial state as an MPS. By assumption, it can be done. Okay? And then we take this time evolution, which looks like a big matrix, and we never build this big matrix. What we do is we break this time evolution into small time steps. And there is something called the Suzuki-Trotter decomposition that says that if I have minus I h epsilon, okay, so a small time evolution, this can be broken into, so what do we have now? We have the Hamiltonian sum of local terms, say nearest neighbors. Then we can reorganize it into part A and part B, where A contains odd links and B contains even links. So we can break this into, let me do it explicitly. We have H, which is sum over nearest neighbors, okay? And now I break it as sum over I being odd, hi plus 1, and I being even of hi plus 1. And here we have h12, h34, h56. All these terms here commute with each other, okay? Because they are acting on different sets of sites, 1, 2, 3, 4. There is nothing acting between 2 and 3 because it's in here instead, okay? So let me call this A. Let me call this B. And it turns out that this can be, there is this Trotter decomposition that tells you that this is approximately A epsilon B epsilon plus higher order epsilon squared, okay? And using this type of decomposition, what you can do is instead of writing this huge unitary evolution, which we could not afford because this has dimension 2 to the n times 2 to the n, or d to the n times d to the n, instead of writing this big object, we can replace it with just multiplying this MPS times this part, this MPS times that part, and so on. Okay, we can Suzuki-Trotter decompose this time evolution, and what that looks like is actually something like this. This would be acting with the odd terms, and then react with the even terms. And so on. So we don't have this expensive expression. We have something that it's a decomposition with a number of parameters, which is again order n. Because of this direction, there are n times how many we need, which will depend on the time. So order this number of parameters. We have this tensor network. And this, in principle, in general, it cannot be contracted efficiently. Okay, it would have an exponential cost. But now what we will do is we'll proceed step by step. We'll first multiply the MPS with the first row, and then the second row, and so on. And by assumption, all the intermediate states that we are creating, so the result of multiplying the MPS with the first row, is also does not have a lot of entanglement. So we will find a way of writing it as an MPS. Then we'll multiply this resulting MPS times the next row. The result will be a state that by assumption doesn't have a lot of entanglement, so it can be represented with an MPS, and so on. So we'll manage to take different rows of gates, multiply it by the MPS, and replace the result with a new MPS, and proceed sequentially, okay, ordered t times. And that's how we can efficiently simulate time evolution in the quantum system. Okay? Very good. So, and I want to mention that actually we've been talking about Hamiltonians in 1D, but MPS strategies are also used in quantum chemistry, for instance, okay? Or in statistical mechanics, in many places. In mathematics now, they are called tensor trains or something like that. They've also been investigated independently by mathematicians more recently. And so in quantum chemistry, what you have is maybe if you had a polymer of some form, okay? This is not a tensor network, even though I'm using circles and legs. That's because that's how they draw it. If you had a polymer, that would be, roughly speaking, a one-dimensional structure. And it's no surprise you have electrons sitting near these atoms or ions. And then you would like to understand the wave function of an electron that is sitting here. So you will have a many electron problem here. And what you do is you use an MPS that follows some path. Okay, so this would be the index of your MPS. And then you have tensors that are devoted to each of the electrons that you have here. The idea is that you can use the MPS structure to follow the structure of the molecule. Okay? And again, you can always do that because we argued that an MPS decomposition is valid for any wave function. Okay? But the big question in quantum chemistry is whether a chi one dimension is smaller than exponentially the system size will appear as a result when you decompose the wave function in this way. And what happens is that, yes, that it so happens that even though it's not obvious in this case, the entanglement, again, does not grow as much as it could. It's the entanglement of the wave function in this molecule is still smaller than what you would have in a generic state, and therefore, using a matrix product state is again of interest and beneficial. Okay, so, and just to complete my list, because it's time to finish, I'll say that we can also use matrix product states for two-dimensional systems. And again, all we do is we put our two-dimensional lattice, even though something is going to go terribly wrong, we can try this, and then this time we'll use our MPS. It's going to be some tensors that we put here. So there are sides. Each side has spin 1/2 degree of freedom or whatever. And then our MPS is going to snake around the lattice. Okay? So this is, again, one of the methods that in tensor networks that are used to study two-dimensional systems. It's not ideal. We'll see on Friday that there is a more natural tensor network to use for two-dimensional systems, but you could, in principle, do that. And the problem here is that this bond dimension, so the bond dimension that you have when you cut the system into two, you see that there is a unique bond dimension going across the cut, maybe from this tensor to the next one. And this bond dimension here, has a chi that has to account for an area law of entanglement in the ground state. Remember, this is a two-dimensional system. There is some length here, Ly. And what we have is that the entanglement entropy between this part of the system, between the left and the right of this cat, is linear in Ly. And that implies, remember chi, roughly speaking, goes as the exponential of the entropy. And this entropy fulfills an area law. So area law in 2 dimensions means that this entropy grows linear. So entropy is proportional to Ly. That's the size of the boundary between left and right. And so what this means is that we have a cost which is exponential in Ly. Okay? So it means that it's not going to be efficient, right? It's exponential in Ly. The cost is, so cost is exponential in Ly. But what should we compare this cost against? Well, what's the cost of writing the wave function on the whole system? If we didn't use an MPS, it turns out that it's d to the size of the system, which is Lx times Ly. Okay, so this is exponential in Lx Ly. So an exact diagonalization would have exponential in the product of Lx Ly. An MPS gives you a cost which is exponential only on Ly. So you still save a lot. Okay? So in 2 dimensions, MPS cannot be scaled arbitrarily. There is an exponential cost growth of the cost with the y direction of the 2-dimensional system, but still it gives you a huge advantage with respect to exact diagonalization techniques, and that's why we still use MPS in 2 dimensions. Okay, very good. We'll continue tomorrow.